Hi everyone, thank you for coming to this presentation, for listening to this presentation online. I'm going to be talking about the intensification of mesoscale eddies in the western Arctic Ocean as we can observe it from spinning of ice floes. So this is a work done together with Rosalinda Lopez Acosta and with Monica Martinez Wilhelmus. And I want to thank our sponsors, ONR and NSF, for providing funds to do this research. So before I talk about our methodology, just a few slides to briefly introduce you to the area of the Beaufort Gyre and why we care about eddies and sea ice together. So a few studies, some years ago already, 2016, there a few studies appeared that talked about the equilibration of the Beaufort Gyre under surface stress forcing, and this is basically the halocline, and there is surface convergence of freshwater, and there is Ekman pumping associated with it. And the question was how deep this halocline is and what stops this halocline going all the way to the bottom. So one of the answers were provided in these papers here, which say that there's a balance between the Ekman pumping and the counteracting eddy overturning. So similar balance occurs in Southern Ocean if you're more familiar with that literature. So a few years later, several more studies appeared, which basically looked into another idea that says that the ocean stress is composed of two components, atmospheric stress and ice ocean stress. And the ice ocean stress depends on the ocean itself, right? Such that when you speed up the velocity, the ice will be slowing down the ocean rather than spinning it up, such that these two stresses will start opposing each other. And eventually the Ekman pumping will be shut down, and that creates conditions for equilibration of the gyre. So these two hypotheses basically can live together technically, but the idea is that several studies show that eddies actually play a very minor role in this equilibration. So I want to point your attention to this study over here by Armitage et al. 2020. This is where the authors looked into cumulative kinetic energy sources and sinks and compared how much energy does the gyre receive versus how much energy is being stored in available potential energy. So there are a few curves over here, but the blue curve over here shows the ice ocean stress work, which is negative, meaning that ice is basically slowing down the geostrophic flow. The atmosphere ocean stress is positive, and then the total is also positive, and most importantly it's staying positive and accumulating with time. When we look at the cumulative potential energy, energy is actually being stored, quite a lot of it, about 20 or 30 petajoules for the entire area of the Beaufort Gyre. And the estimate of this study of the residual of energy sources versus what's been accumulated has been hypothesized to be associated with eddies, and this is the purple curve over here. And as we can see, the purple curve, which is the cumulative energy that must be dissipated, presumably through eddies, and to get to the actual energy that's been stored, you need only a few years of this eddy dissipation. So the authors here, one of them hypothesized that the energy is being dissipated by Bernoulli instabilities taking energy from available potential energy and putting it into the kinetic energy that is dissipated in the surface mixed layer. All of this is all nice hypothesis. The problem is that we don't have comprehensive observations of eddies all throughout the gyre. So we took a creative approach here. So we decided to look and to make use of the fact that sea ice is a granular media, and sea ice is being split into many chunks, especially as the ice comes out of the winter to springs. and the waves coming in and they destroy the ice and make it smaller and smaller pieces, and some of these pieces we can detect with observations and we can look at how they move. And turns out, as you will see with this at the end of the talk hopefully, that the motion of these flows can be linked to eddy activity underneath it. So here I just show an example of Amodius reflectance images piled into a video, where if you can focus, for example, on this pair of flows over here, you see that they're counter-rotating, and flows over here, which are in strong contact with each other, they're kind of moving all together as one big solid body because of these tight interactions between each other. Once you leave the flow alone, it starts rotating quite a bit, and we claim that this rotation is in the response to sea ice, to eddies moving the sea ice. So to demonstrate that, we can create a simple model where we put some sort of shape of an ice flow that's being diagnosed from or segmented from the reflectance images, and we can just force it with atmospheric winds and ocean stresses over an eddy in ocean to see what is the rotation of this flow doing when it's not hitting other flows. So we solve these simple equations for the center of mass and for the angular velocity of the flow, and we find that very simply the answer here is that whenever you hit an eddy, the flow rotates in the same sense as the eddy does. Moreover, this is very quantitatively accurate too. So let me demonstrate with this video. So here on the x-axis we plot the flow rotation rate taken as basically d by dt of its angular position, and on the y-axis we plot the vorticity of the ocean that is averaged over the surface area underneath the flow, right? So each point over here represents some sort of randomly chosen flow from the data set of many flows that we have, and then put in a random location in the ocean with a random vorticity to begin with. As time goes by, after about 2-3 hours, we see that the two metrics correlate really well, and we make use of this fact to basically look into the flows and to see what kind of ocean corresponds to what kind of ocean eddies can give us the vorticity of the flows. So to do that, we need to identify a whole bunch of flows in marginalized zones over a whole bunch of years of data, which we did using this methodology developed by Rosalinda. It's basically a method to go from the image on the left, where you have just reflectance with some clouds partially overlapped, and then identify only those flows that you can track in time by matching their shapes. So if the flow is preserving their shape over a few days and you can detect that it's the same exact flow, there's some criteria for that, you're good to go. So to demonstrate you a few examples over here, here is an example of a flow. You can look by eyes, you don't need a segmentation algorithm. You see that it's rotating counterclockwise, and quite a bit actually. So in a matter of just one day it can rotate by 45 degrees easily. This flow is about 20 kilometers in size. There are other flows next to it that rotate in different directions, right? And technically we claim that this flow is not really interacting with other flows. It's not perfectly possible to eliminate all interactions. There will be some tiny flows overlap interacting with it, but tiny flows provide only tiny correction to the torques. So we consider these flows that are not interacting with other large flows as free drifting flows. If we look at trajectories, and this is important, you can see that the flows are translating in space, yet their rotation rate can change, and it changes sign. So with color, what's plotted is the rotation rate over here. So red is the positive rotation, blue is the negative rotation. And as you can see, the rotation rate persists over many days. So each snapshot here is 1 day. Each flow location is shown 1 day. So what happens here is that the flow is being translated by the action of winds, but winds are not rotating the flow. Winds are only moving this flow as in a translational way, whereas the underlying eddies are moving the flow, and as long as the flow is over an eddy, it very quickly, within hours, picks up the rotation rate and starts rotating. And then as the atmosphere pushes the flow away from an eddy, then it will pick up rotation of another eddy. So that's what's happening here. So this slide over here shows basically the vast amount of flows that we have diagnosed and their rotation rate. So this is observation count plotted within a beam that is 25 by 25 kilometers size, and in total by years we have thousands of rotation rate observations. We have some consistency with existing knowledge of eddy dynamics in the Beaufort Gyre. We look into the dominance of, we also get in the predominance of anticyclonic eddies, although not as much as literature suggests. So our split is roughly like 2/3 to 1/3, whereas in literature we get an overwhelming dominance of anticyclones. This has to do with the fact that we're still at the surface, we're not yet in the interior of the gyre. And there's probably some mixture of interior gyre of the gyre eddies that have surface expression, plus mixed layer eddies that are generated at the surface. And perhaps the most important figure is this one, where we demonstrate, and I'm going to show it again for you. So you're going to look into how the variance of rotation rates, plotted on x-axis, change with the length scale of the flow. And the idea here is that the flows rotate really fast when they're small, and the bigger flows rotate smaller, much like in the ocean, where we have big eddies having low Rossby numbers and low rotation rates, and small eddies have high rotation rates. And this is associated with the fact that the entropy, which is vorticity squared, is cascading towards smaller scales in the ocean. So small eddies are more likely to have higher rotation rate than big eddies. To proceed with understanding what the ocean characteristics might correspond to the observed dependency between the variance of the flow rotation rate versus the length scale over here. So this figure looks like that. Basically, the smaller the length scales are, the larger the rotation rates are. So this is the inverse length scale here. What we do is we build a model of eddy dynamics, which is the standard model, two-layer quasi-geostrophic model of Berkeley instabilities, and it's flexible enough with those parameters over here, the deformation radius, the difference between the Berkelinicity, delta U, and the relative thickness ratio between the two layers. With those three parameters, it's flexible enough to generate a vast number of characteristics of eddies. You can have strong eddies, big ones, you can have elongated eddies, whatever you want can come out of this model. Well, not whatever you want, mostly in the mesoscale range, whatever you want. What we find is that we can use the observations and adjust these parameters to see if we can have a best fit parameters that will match the observed behavior of flows and the synthetically generated curve that tells us the variance as a function of length scale, where synthetically generated flows are basically those flows that we take from observations, put them into our model, ask them to rotate around, and then construct this curve over here. So this is the best fit flow of vorticity shown over here. The best fit image of vorticity, and this is one representative snapshot. You can have a lot of them with those parameters. And the point here to take home is that there are eddies of different sizes. You have smaller scale features over here, which are about tens of kilometers, and then you have larger scale features over here, which could have the extension of the strong azimuthal velocity going all the way to about 60-80 kilometers, but not necessarily bigger than that. So there are no eddies that are 200 kilometers in size, at least over here. They're not evident. So, oh, and one more thing to look into is that once we have the model, what we see is the dissipation rate, which is the key thing. Dissipation rate associated with ice ocean stress is about 0.7 milliwatts per meter squared. And if we compare it with the estimate of Armitage et al., that was based using completely independent data set, we find that this number corresponds to about 100 petajoules of energy that ice dissipates, eddy kinetic energy that ice dissipates in 5 years. And this is to compare with this number of about 40 petawatts that was estimated in Armitage et al. So these two independent methodologies actually agree to an order of magnitude with what is expected to be dissipated by eddies by the ice ocean drag. So finally, I wouldn't sleep well if I would not find a method to independently validate directly the kinetic energy that we found reconstructed from the data from the rotation of ice floes. And what I've done is that I looked into EKE relation with the ocean variance, with the variance of rotation rate of flows, and those two lines represent the surface and subsurface EKE. And it basically says if the flows are rotating fast, there must be a larger EKE here. Note that subsurface EKE, surface EKE is much smaller than subsurface EKE. So using this linear relation, what we can do is we can go to regions which are on top of moorings, and we have 4 Beaufort Gyre moorings that has some lengthy time series record of velocity, and we can reconstruct basically the predicted subsurface EKE based on our whole methodology of taking flow rotation, running the QG model, finding best parameters, and figuring out what EKE is. And then we have an independent measurement here from the mooring. So this 1-1 line over here, not a fit, it's really is a 1-1 line, and this figure I made at the final stage without readjusting any parameters, and I didn't touch anything, so this is a true test to the methodology. A few points that are corrupted, mooring observations outliers. This point is not corrupted but still is an outlier, but most of this point lie on 1-1 line. And again, to stress that these two things are completely independent data sets. So if we can trust this method, and I hope you do, by now we can look at how the reconstructed variance of flow rotation rates, which is linearly correlated with EKE, how it's connected with the large-scale circulation, which is the Beaufort Gyre strength. Again, this figure is very complicated, but hit the pause button, figure out what the axes are. There are a few axes to pay attention to. The blue one over here shows the sea surface height index of the Beaufort Gyre. Basically, the stronger the Beaufort Gyre, the larger the blue line will be, the larger the sea surface height anomaly it will have. We have the mean flow velocity, which is one of these red lines over here. We have also the variance, which is this red curve over here, and the variance extends all the way to 2021. Actually, we're going to put a few more dots very soon here. The point to make here is that all these characteristics of the mean flow are correlated very tightly with the variance of flow rotation rate. Correlation coefficients here are 0.8 or something like that. And most of all, the flow rotation rates, since we know the time series over here, they have the decadal trend going upwards, meaning that these days, in the starting from 2016 onwards, on average the flow rotation rates are quite significantly higher than they used to be pre-2008 or something like that. And this change is associated with the drop in the amount of sea ice that's shown here in gray bars. So the sea ice is dropping and flow rotation is going up. The sea ice increases, flow rotation goes down. And since on the decadal trend in sea ice concentration and sea ice area coverage in the Beaufort Gyre is going down, we are observing both intensification of the variance of flow rotation rates and hence the kinetic energy is amplifying. So conclusions fairly quickly, because I'm running out of time. I may have already run out of time, but conclusions are the following. We have a methodology of looking at sea ice to figure out and how individual flows rotate, and to figure out what the eddies are doing underneath. We have done that. We have provided an estimate of what the ocean eddy field should look like under the sea ice. And what we find is that just within 2-3 years, it is enough for the EKE, eddy kinetic energy dissipation associated with ice ocean drag, to completely drain the Beaufort Gyre available potential reservoir. So this is on par with what we think the gyre equilibration timescale is, and hence eddies must be part of the gyre equilibration process. So this study is perhaps the first one that is so directly proving this point. And then also we find that, of course, with continuing global warming, if winds are going to continue blow with the same rough strength over the Beaufort Gyre, then we expect the gyre to spin up quite significantly. So those of you who are modelers or paying attention to model developments, well, climate models are still ignoring sea ice in eddy parameterizations, because mesoscale and sub-mesoscale eddy parameterizations have been developed without taking care of ice at all. And as we demonstrate here, the EKE at the surface and overall through the entire water column matters quite a lot when it comes to the presence of sea ice. This is simply because the sea ice is very efficient in dissipating EKE right where it's at its maximum, which is at the very surface of the ocean. So there's some work in progress, and hopefully at next meetings I will tell you about our parameterizations in both mesoscales and sub-mesoscales. Thank you for your attention, and hope to hear from you with questions. Bye.